Okay, what if I told you that one of the simplest shapes you can possibly imagine, the humble cube, is actually the secret key to solving ancient math puzzles, building futuristic cities, and even, get this, structuring the absolutely bizarre world of quantum computing? It sounds a little crazy, I know, but let's dive.
So we all know the Rubik's Cube, right? It's that classic, maddening puzzle. But when it first came out, people weren't just stuck on how to solve it. No, they were completely baffled by how it could even exist in the first place. The way it holds itself together while twisting just seemed impossible, which, led to this very direct and honest reaction. It's a perfect little machine.
And here's the best part, the real twist. It was never even supposed to be a toy. Erno Rubik, he was an architect, and he was just trying to solve a very real structural problem. How do you get a set of blocks to move around on their own without the whole thing just falling into a heap? So he builds his prototype, he gives it a scramble, and bam. He realizes he has a brand new problem. He can't get it back to how it started. It actually took him a full month to solve his own invention. And somewhere in that frustration, he had this amazing realization. He hadn't just solved a structural challenge, he'd accidentally created the world's most famous puzzle.
So that origin story, it really sets the stage for everything we're going to talk about. We're going to look right past the colorful stickers and explore the cube for what it really is. A brilliant solution to a puzzle of pure structure.
And this is the core idea, the big takeaway. The cube isn't just a six-sided object. It's a powerful mental model. It gives us concepts like modularity and defined space, this whole system of interchangeable parts. And we use these ideas all the time to take these incredibly complex, messy problems and sort of wrestle them into a shape that we can actually understand and manage. All right, so let's see how this whole building with blocks idea actually plays out. We're going to take a trip through the centuries, starting with some pretty abstract math and ending up with the marvels of modern architecture.
You know, this idea of thinking in blocks, it isn't new at all. It's ancient. Way back in the 11th century, you had the polymath Omar Khayyam using literal cubes to visualize and solve algebraic equations. Then fast forward a few hundred years, you have Oliver Byrne using colorful shapes to make geometry way more intuitive. And now, today, we're using that very same core idea to assemble entire skyscrapers, basically like giant Lego sets.
Now, stop and think about what this really means for a second. When Omar Khayyam saw an equation with something like x squared or x cubed, he didn't just see symbols on a page. No, he saw a literal physical square area, or a physical cubic volume. He was solving these equations not just with algebra, but by figuring out where actual shapes, like parabolas and circles, would physically intersect. He turned abstract math into something you could almost touch. And this is where you see this amazing 1,000-year-old thread connecting these two worlds. On the one hand, you have Khayyam, who used tangible geometry to solve the abstract equations of his day. And now, today, architects and engineers are doing the exact opposite. They're using abstract tools, like this 3D modeling software, to solve the very real, very tangible structural problems of building our world.
This modern approach is called volumetric modular construction, and it is an incredibly efficient process. We're talking about building huge sections of a building, basically giant steel cubes, and getting them 90 to 95% finished inside a factory. That includes the plumbing, the wiring, the windows, even the furniture is pre-installed. It's wild.
Then, these finished blocks, they get shipped to the construction site and are just snapped into place. What you're looking at here is the pizza structure. And yeah, that's its real name, where these modules are placed around a central core that's already been built. This is literally building with blocks, just on a massive scale. It's solving the exact same puzzle that Erno Rubik was tinkering with.
Okay, so if the cube can help us structure the world we can see, can it also help us structure the world we can't see? Let's push this idea to its absolute limit and tackle the ultimate design challenge, the incredibly strange, chaotic world of quantum computing. So in the quantum world, the basic building block isn't a bit, it's a qubit. Now, a normal computer bit is simple, right? It's just an on or off switch. But a qubit, well, a qubit is much, much weirder. Thanks to a wild property called superposition, a qubit can be a 0, it can be a 1,
or it can be both of them at the exact same time. Here's a really simple way to think about it. A classical bit is like a light switch. It's either on or it's off. A qubit is more like a dimmer switch. It can be fully on, fully off, or any value in between, and it can be all of those at once. That ability to explore tons of possibilities simultaneously is where a quantum computer gets its incredible power. But all that power comes with a monumental problem. Qubits are unbelievably fragile. I mean, their quantum states are just probabilities, and they can collapse if you so much as look at them wrong. So the real question becomes, how in the world do you build a reliable computer out of something that is fundamentally pure, untamable chaos? This is what that hardware actually looks like. It's this incredibly intricate web of superconducting circuits that have to be kept in almost total isolation at temperatures that are literally colder than deep space just to keep those delicate quantum states from disappearing. It looks ridiculously complex because it is ridiculously complex.
So you're faced with this almost unimaginable complexity. How do you even begin to tackle it? Well, researchers are turning back to our fundamental tool. To try and tame the quantum realm, they are structuring their thinking, you guessed it, in cubes.
It all starts by creating a totally new kind of blueprint. I mean, if you're going to build something this complicated, you first need a really organized inventory of all the parts. So, new frameworks are being developed to do just that. They break down completely different domains, like physical space, symbolic language, and the quantum world, into their most basic building blocks, their primitives. The goal here is to create a universal, structured language that can describe everything from a single particle to a whole paragraph. And you can see this principle of structured modular thinking pop up in the hardware designs themselves. On the right, there's our modular building again. And on the left, that's a proposed design for a scalable quantum computer. It is the exact same logic. You create these stackable, interconnected modules that can protect the fragile bits and allow the whole system to grow. It's cubic thinking, just applied at the quantum scale. But maybe the most mind-bending application of this is something called the cubic glyph lattice. This is basically a tool for designing quantum software. See, since the hardware is so complex and often doesn't even exist yet, developers need a way to build their programs conceptually. So they imagine this virtual 3D grid, like a wireframe cube. They place their virtual qubits at the corners, and then they use these symbolic commands or glyphs to map out all the interactions along the edges. It's like creating a perfect 3D blueprint for a program before you've even laid a single brick of the foundation. So we've watched the cube evolved, right? From this accidental puzzle to a tool for architects, all the way to a blueprint for quantum logic. It's become so much more than a shape. It's become a fundamental way that we impose some kind of order on reality itself. The legendary physicist Richard Feynman once famously said, "I think I can safely say that nobody really understands quantum mechanics." And he was right. Our brains just did not evolve to make sense of its completely bizarre rules. And that's exactly why we need these mental models. We need structures like the cube to give us a foothold when we're dealing with the incomprehensible. At the end of the day, the cube's real enduring power is its ability to shape how we think. It doesn't matter if you're an ancient mathematician, a modern architect, or a quantum programmer. This one simple shape gives you a framework to structure information, to build with interchangeable parts, and to define a space where chaos can finally be managed. The cube has turned out to be this astonishingly powerful tool for thought. It's helped us build and understand our world in ways its inventor could never have dreamed of. And that just leaves us with one last question to chew on. If the cube helped us structure our world, what new shapes, what new mental models are we going to need to invent to imagine the worlds of tomorrow?